You remember the past. You do not remember the future. This feels so obvious that it is almost foolish to say out loud, and yet it hides one of the deepest puzzles physics has never solved. Because the laws that govern every particle in your body do not know the difference between past and future. Run them forward, run them backward, and both are equally legal. There is no rule that says memories must form in one direction, no equation that points from yesterday toward tomorrow. The arrow you feel so certainly, the one that lets you regret what happened and wonder what comes next, is nowhere in the rulebook of the universe. And when you chase it all the way down, past the cooling coffee and the breaking glass, it leads somewhere astonishing, all the way back to the very first instant of the cosmos, to a state so impossibly ordered that no one has ever been able to explain it. Make yourself comfortable. Subscribe if you have not yet, because by the end of this, you will see that the reason you cannot remember tomorrow reaches back 13.8 billion years. Let us slowly slip into this. Part 1. The one thing you are sure of. There is one fact about the universe that you have never once doubted. Time moves forward. You feel it in the most ordinary moments of your life, in the cup of coffee on the table beside you that started out hot and is now slowly going cold, in the way the light outside the window slides from afternoon into evening, in the simple certainty that whatever you did this morning is finished and cannot be undone. You do not need a physicist to convince you of this. You have known it since before you had words for it. The past is behind you, fixed and unreachable, and the future is ahead of you, open and unknown. And between them, there is a thin, moving edge you call now, sliding always in the same direction, never pausing, never turning back. Of all the things this channel has ever asked you to question, this one feels the least negotiable. We have talked about space having no center, about there being no universal present, about the future already existing, in some sense, inside the geometry of space-time. Those ideas are strange, but you could hold them at arm's length. This one is different. This one is happening to your body right now. You are aging in one direction. Your memories accumulate in one direction. Every breath you take goes from inhale to exhale, and never the reverse. The forward motion of time is not an abstraction you read about. It is the medium you live inside. And yet, when you look closely at why time moves forward, something deeply unsettling happens. The certainty does not get stronger the closer you look. It gets weaker. Because when physicists go searching for the source of this most obvious fact, the place where the direction of time is written into the laws of the universe, they find that the place is empty. The arrow you are so sure of is nowhere to be found in the fundamental rules. It is as if you walked into a room you had stood in 1,000 times, looked down, and discovered there was no floor, only the long habit of never having looked. Consider how thoroughly the forward direction of time saturates everything you know. A glass falls from the counter and shatters into 100 pieces across the kitchen tile. You have seen this happen. You have never, not once in your entire life, seen the reverse, the 100 pieces gathering themselves up off the floor, leaping back to the counter, and fusing into a whole glass. A drop of ink spreads through a glass of water until the water is evenly coloured, and it never gathers itself back into a single concentrated drop. Smoke rises from a candle and disperses into the air of the room, and it never funnels back down into a tidy plume and dives back into the wick. Heat flows from the hot thing to the cold thing, warming your hands on a mug, and never the other way. Every one of these processes has a direction, and the direction is always the same. We give this one-way quality a name. We call it the arrow of time. The phrase comes from a British astrophysicist named Arthur Eddington, who introduced it in a series of lectures he gave in 1927, later published as a book called The Nature of the Physical World. Eddington wanted a way to talk about the fact that time, unlike space, seems to point. You can travel left or right, up or down, forward or backward through space, but through time you can only go one way. Eddington said that this arrow is not drawn by any single event. It is drawn by something happening across the entire universe at once, a quantity that is always increasing, never decreasing, a quantity that he believed was the true source of time's direction. We will come to that quantity soon, and we will spend a long time with it, because it is the strongest answer anyone has ever found. But I want you to notice something about it first. Eddington did not locate the arrow of time in the laws of motion. He located it in a tendency, a statistical drift of the whole world from one kind of state to another. That choice was not an accident. It was forced on him, and on everyone who has thought carefully about this since, by a problem that sits at the very bottom of physics, a problem so simple to state and so hard to resolve that it has survived every advance in our understanding of the universe for more than 150 years. The problem is this: the laws that govern the individual pieces of the world do not care which way time runs, but the world those pieces build does. And nobody has ever fully explained how you get the second thing from the first. There is something worth pausing on in just how one-sided your evidence is. In your entire life you have witnessed an uncountable number of these one-way events. Every meal that cooled, every ice cube that melted, every breath of warm air that vanished into a cold room, every drop of colour that spread through water, every fire that turned wood into ash and smoke, and never the reverse. Hundreds of such events every single day, for as many days as you have been alive, and across all of them, without a single exception, the direction has been the same. You have never once seen the film run backward. No one has. In all of recorded history, across every human being who has ever lived and everything they have ever watched, the count of spontaneous entropy decreasing events, eggs unbreaking, smoke ungathering, heat flowing uphill on its own, stands at exactly 0. That is not a mild statistical preference. That is a regularity so absolute that it feels like a law. And the strange thing, the thing we are going to spend the night on, is that it is not a law, or at least not a law in the way you would expect. It is something subtler and, in a way, far more remarkable. Notice, too, that the arrow shows up not only out in the world, but inside your experience of it. You do not merely observe that eggs break. You feel time passing. There is a sensation of a moving present, a now that slides steadily forward, leaving each moment behind as it goes. You anticipate the future and you remember the past. And these two mental acts feel completely different. One, a kind of darkness you lean into, the other, a lit room you can turn and look back at. Even your emotions are time-shaped. You can regret what has happened and dread or hope for what has not. All of this, the felt flow, the asymmetry of memory and anticipation, the very texture of being a conscious creature, rides on the same arrow as the cooling coffee, and by the end of tonight you will see that this is no coincidence, that your inner sense of time and the breaking of the egg are powered by the very same thing, traced all the way back to the same astonishing source. Tonight I want to take you all the way down to the bottom of that problem. I want to do it slowly, because it deserves to be done slowly, and because the deeper we go, the stranger it becomes, and the strangeness is easier to sit with when you are not being rushed. We are going to take the question apart the way you might take apart a watch that runs perfectly but that nobody can explain. We are going to lay out the popular answers one at a time, the ones you have probably heard, the ones that sound right. Time is just change. Time is entropy. Time is what memory measures. Time is the expansion of the universe. We are going to test each of these the way an investigator tests a suspect, patiently, looking for the place where the story breaks down. And what we are going to find, again and again, is that each answer when you press on it hard enough, hands the question to something else, and that something else hands it on again, until every road we walk down arrives at the same locked door at the very beginning of the universe. By the end of this, I do not think you will be more certain about why time moves forward. I think you will be less certain, and I think you will be glad of it, because the uncertainty is the honest part, and it is far more interesting than the false comfort of a simple answer. The forward motion of time is the most familiar thing in your life, and one of the least understood things in all of science. Those two facts living side by side is the whole story. So get comfortable, and let us begin where you already are, inside the certainty, and watch what happens as we start, very gently, to take it apart. Part 2. The laws do not agree. Let us start with the rules. If time has a direction, the most natural place to expect it would be in the fundamental laws of physics, the equations that describe how the pieces of the world move and interact. These are the bedrock. Everything else, every chemical reaction, every beating heart, every collapsing star, is built out of particles obeying these laws. So if the universe has a built-in arrow pointing from past to future, surely it would be written there, in the rules that govern the smallest things. This is the obvious place to look. And when you look, you find nothing. The arrow is not there. Take the oldest and most familiar set of laws, the ones Isaac Newton wrote down in the 1680s, to describe how objects move under forces. Newton's laws have a property that mathematicians call time reversal symmetry. What it means is simple and astonishing. Imagine you film a few billiard balls rolling across a table, colliding, scattering, bouncing off the cushions. Now play that film backward. Here is the remarkable thing. The backward film shows motion that is also perfectly legal under Newton's laws. Every collision in reverse still conserves momentum and energy. Every trajectory in reverse is still a valid solution to the equations. If you handed the backward film to a physicist who did not know which way it was meant to run, there would be no way, from the physics alone, to tell. Both directions obey the same rules exactly. The laws of motion do not prefer one over the other. You might think this is a quirk of Newton, a feature of an old theory that newer physics would correct. It is not. The same symmetry shows up everywhere. The equations James Clerk Maxwell wrote down in the 1860s to describe electricity and magnetism and light are time reversal symmetric. Albert Einstein's theory of general relativity, which describes gravity as the curving of spacetime, is time reversal symmetric. The Schrödinger equation, which governs how quantum systems evolve, the most fundamental description we have of matter at the smallest scales, is time reversal symmetric. Run any of them forward, run them backward, and both directions are equally valid physics. At the level of the individual particle, the individual field, the individual quantum wave, the universe has no idea which way time is supposed to go. It helps to make the reversibility concrete, because it is so easy to nod at and so hard to truly believe. Imagine two billiard balls on a frictionless table. One rolls toward the other, strikes it, and the two scatter apart at some angle, each carrying away part of the original motion. Film it. Now run the film backward. What you see is two balls rolling toward each other from those scattered directions, colliding, and one of them stopping dead while the other rolls smoothly away. Is there anything illegal about that? No. It conserves momentum. It conserves energy. It is exactly what would happen if you had set those balls moving that way to begin with. Every individual collision, every bounce off a cushion, every trajectory is perfectly happy running in reverse. This is true of 3 balls, of 10, of the whole rack scattering from a break. The microscopic motions are reversible all the way down. And yet you know, watching a real game of pool, that the break, the moment the cue ball smashes the tidy triangle into chaos, looks utterly different from its reverse. You would never see 15 scattered balls roll back together into a perfect triangle and eject the cue ball at exactly the right speed. The collisions permit it. The world refuses it. There, in miniature, is the whole puzzle. There is a deeper and more precise version of this statement, and it is worth knowing because it closes off almost every escape route. In the 1950s, physicists proved something called the CPT theorem. It says that any sensible theory of quantum fields, which is to say the entire framework underlying modern particle physics, must be exactly unchanged under a particular combined operation. The operation is this. You swap every particle for its antiparticle, that is the C, charge conjugation. You flip space as if reflecting it in a mirror, that is the P, parity. And you reverse the direction of time, that is the T. Do all three of those things together, and the CPT theorem guarantees that the physics comes out identical. This is one of the most thoroughly tested results in all of science, and it has never once been found to fail. The rulebook of the universe is, to overwhelming precision, blind to the direction of time. So here is where we stand, and I want you to feel the full strangeness of it. Every law we have, from the motion of planets to the behavior of the tiniest quantum particle, treats past and future as interchangeable. There is no fundamental equation that says heat must flow from hot to cold rather than cold to hot. There is no fundamental equation that says the glass must shatter rather than reassemble. The microscopic rules permit the reverse of everything you have ever seen, just as readily as they permit the thing you actually saw. And yet you have never seen the reverse. The shattering happens, the reassembling never does. The asymmetry that rules your entire experience of the world is not in the laws, it is somewhere else. The question is where. This is the central puzzle of the arrow of time, and I want to state it as plainly as I can, because everything that follows is an attempt to answer it. The fundamental laws are reversible. The world they build is not. Somewhere between the particle and the person, between the reversible rule and the irreversible reality, a direction appears that was nowhere in the rule. Where does it come from? How does a one-way world get assembled out of two-way parts? That is the question. And notice already what we have learned, even this early. Wherever the arrow comes from, it is not a basic law of nature. It is something that emerges, something that appears at the level of large collections of things and is simply absent at the level of their individual pieces. The asymmetry is not in the laws. Hold on to that phrase. We are going to return to it, and each time we return, it is going to mean something heavier than it did before. There is a word physicists use for this kind of thing, and it is worth introducing because it reframes the whole puzzle. The arrow of time appears to be emergent. An emergent property is one that does not exist at the level of the individual parts, but appears only when enough of them come together. A single water molecule is not wet. Wetness is something that emerges from many molecules acting together. A single molecule of air has no temperature and no pressure. Those are properties of crowds. The arrow of time looks like it belongs to this family. No single particle has a direction in time. No fundamental law has one. But assemble enough particles into a glass, an egg, a cup of coffee, a brain, and a direction appears, sharp and unmistakable, a one-way street that none of the underlying pieces possessed. This is a genuine clue, and it points us away from the laws and toward the collective, toward what happens when astronomical numbers of reversible parts move together. That is exactly the territory of statistics and probability, and it is where, in the 1870s, the strongest answer to our question was born. So the failure to find the arrow in the laws is not really a dead end. It is a signpost, telling us to stop looking at the parts and start looking at the crowd. Now, a careful person might object at this point. Maybe, you could say, we just have not found the right law yet. Maybe there is some deeper equation, not yet discovered, that does pick a direction in time, and once we find it, the whole mystery dissolves. This is a serious possibility, and we will give it its due later. because there is in fact one tiny, strange place in physics where the laws do seem to flinch, where time reversal symmetry is very slightly broken. It was discovered by accident in 1964, and it won a Nobel Prize. And when we get to it, you will see why it is both the most tantalizing clue in this whole story and, almost certainly, not the answer. But that is for later. For now, take the laws at their word. They are reversible. They do not know which way time goes. And so, if we want to understand the arrow, we have to stop looking at the rules and start looking at something else. We have to start naming suspects. And the first suspect is the simplest one of all, the one most people reach for without thinking. Maybe time moving forward is just another way of saying that things change. Part 3. The first suspect time is just change. Here is the first answer, and it is the one that feels almost too obvious to say out loud. Time moves forward because things change. The leaves fall, the candle burns down, the child grows up. Without change, the thought goes, there would be no time at all. And since change is everywhere, time is everywhere, carrying us forward. This is an old idea, older than physics. The philosopher Aristotle, more than 2,000 years ago, defined time as the measure of change, the counting of motion with respect to before and after. A lot of people, when you ask them what time is, will give you some version of this. Time is the thing that happens when things happen. It is change itself. I want to take this seriously, because there is something genuinely right inside it. It does seem to be true that if absolutely nothing changed anywhere, you would have no way to measure the passage of time, and arguably no meaning to attach to it. A universe frozen in a single unchanging instant would have no clocks, because a clock is just a thing that changes in a regular, countable way, and no minds, because a mind thinking is a kind of change too. So change and time are clearly bound together. The relational view of time, the idea that time is nothing but the pattern of change among things, has a long and respectable history, defended by thinkers from Gottfried Leibniz in the 17th century to the physicist Julian Barber in our own time, who has argued that time as a flowing thing does not exist at all, and that all there really is change, configurations of the universe arranged by their similarity to one another. But watch what happens when we ask our specific question of this answer. We are not asking what time is in general, we are asking why time has a direction. Why does it only go forward? And here the answer, that time is change, runs into an immediate and fatal problem. Change, all by itself, does not have a direction. Think about it carefully. A pendulum swings from the left to the right and back again. That is change. Is there anything about the change itself that tells you which swing came first? A planet goes around its star and returns to where it began. That is change. The configuration of the world is different at every moment, yes, but different is not the same as directed. You can have a world full of motion, full of change, in which there is no fact about which way is forward, just as the billiard balls in our reversed film were full of motion, without any fact about which way the film should run. It is worth lingering on the history here, because the debate is old and the stakes were always clear. In the late 17th century, Isaac Newton and Gottfried Leibniz argued about exactly what time is. Newton held that time was absolute, a kind of cosmic background clock ticking uniformly whether or not anything happened at all, a container in which events take place. Leibniz disagreed completely. For him, time was nothing over and above the order of events, the relations of before and after among things that change. Take away the events, Leibniz said, and you take away time itself. There is no empty ticking in the background. This relational view never went away, and in our own era the physicist Julian Barber has pushed it about as far as it can go, arguing that what we call time is an illusion built out of a stack of static configurations of the universe, each one a frozen arrangement of everything, with no genuine flow connecting them at all, only our tendency to read the stack as emotion. It is a serious position, held by serious people. But notice that even in its most radical form, it does not, by itself, hand us a direction. This is the trap in the simplest answer. When people say time moves forward because things change, they are quietly smuggling in the very thing they are supposed to be explaining. They are imagining change as already pointed, already running from a fixed past to an open future. But that pointing is the arrow of time, the thing we are trying to account for. You cannot explain the arrow by appealing to change, because change on its own is just as reversible as the laws that produce it. A film of a swinging pendulum looks perfectly natural, played in either direction. A film of the planets orbiting looks perfectly natural, played in either direction. If change were all there was, both directions would be equally good, and there would be no forward at all. So change cannot be the source of the arrow. Change is real, change is everywhere, but change is symmetric. It happens to point forward only because something else, something we have not yet named, is already giving it a direction. So the first suspect has an alibi. Time may well be bound up with change, but change does not explain why time only runs one way, because change does not run one way. We have ruled out the easy answer, and notice what ruling it out has taught us. The directionality we are looking for is not in motion as such. It is not in the bare fact that things are different from one moment to the next. It is in a particular kind of difference, a difference that has a built-in before and after, a difference that you cannot run backward without something looking wrong. And the moment you start asking what kind of change looks wrong when you run it backward, you are no longer talking about change in general. You are talking about a very specific class of processes, the ones that go one way and never the other. The shattering glass, the spreading ink, the cooling coffee, the dispersing smoke, and what do all of those have in common? This is the question that takes us from the first suspect to the second, from the easy answer to the strong one. Every one of those one-way processes is a process in which something organized becomes something disorganized. The intact glass is organized, the scattered shards are not. The concentrated drop of ink is organized, the evenly tinted water is not. The hot coffee, with its heat gathered in one place, is more organized than the lukewarm coffee with its heat spread evenly through the room. In every case, the forward direction is the direction in which order gives way to disorder, in which things that were gathered become things that are spread out, in which the concentrated becomes the diffuse. That is the pattern. That is the thing that has a direction. And in the 1800s, physicists found a way to make that pattern precise, to put a number on it, to turn this vague sense of order becoming disorder into one of the most powerful and unbreakable principles in all of science. They called the number entropy, and they called the principle the second law of thermodynamics. And for a while, it looked like the answer to everything. Part 4. The broken egg. Let me introduce the second suspect with the homeliest example I can find, because the homeliness is the point. Picture an egg sitting at the edge of a kitchen counter. It rolls, it tips, it falls, and it hits the floor and breaks. The shell fractures into pieces, the yolk spreads, the white runs across the tile. You have seen this. Now picture the reverse. The spilled white gathering itself together, the yolk rounding back up, the shards of shell rising off the floor and knitting themselves into a smooth, unbroken surface, the whole reassembled egg leaping up to settle gently back on the counter. You have never seen this, and you know with total certainty that you never will. The egg breaks. The egg never unbreaks. Hold that phrase in your mind, because we are going to come back to it at the very end of this, and when we do, it is going to carry the weight of the entire universe. For now it is just a simple, true, slightly silly observation. The egg never unbreaks. Why not? The laws of physics, remember, would permit it. Every particle in that reassembling egg would be obeying Newton's laws perfectly. If you could somehow reverse the velocity of every molecule at the instant after the egg broke, the laws of motion would carry the pieces right back together into a whole egg. The reverse process is not forbidden by any rule, and yet it never happens. The answer to why not is the concept of entropy, and it is the strongest idea anyone has ever brought to the problem of the arrow of time. Let me build it up carefully, because once you really see it, a great deal of the world clicks into place. The man who gave entropy its precise meaning was an Austrian physicist named Ludwig Boltzmann, working in the 1870s. Boltzmann's insight begins with a distinction between two ways of describing a system. There is the big picture description, the one you can see, the temperature and pressure and overall arrangement, which physicists call the macro state. And there is the fine-grained description, the exact position and motion of every single molecule, which they call the microstate. The crucial point is that a great many different microstates all look the same from the big picture view. There are countless precise arrangements of air molecules in this room that all correspond to the same macrostate of evenly distributed air at room temperature. You could swap any two molecules, nudge any one of them, and the room would look exactly the same to you. Now here is Boltzmann's idea, written on his tombstone in Vienna as the equation S equals K log W. The entropy, S, of a macrostate is a measure of how many microstates, W, correspond to it. The constant K just sets the units. A low entropy state is one that can be made in only a few ways. A high entropy state is one that can be made in an enormous number of ways, and that is the whole secret. Think about the intact egg versus the broken one. There is essentially one way, give or take, to arrange the molecules into a whole, organized egg sitting on the counter. But there are a staggering number of ways to arrange those same molecules as a mess spread across the floor, all of which look, to you, like the same broken egg mess. The broken state is not preferred because some force pushes the egg to break. It is preferred because, out of all the possible arrangements the molecules could find themselves in, overwhelmingly more of them correspond to broken than to whole. Slow down and watch the glass instead, in the moment it tips from the counter. Imagine you could freeze time at the instant it leaves the edge and see every molecule at once, all of them locked together in the rigid, ordered lattice of the glass, each one held in its place by its neighbours, a single coordinated structure falling as one thing. Now let time move, but slowly, so slowly you can follow it. The leading edge touches the tile. The shock runs up through the lattice faster than sound, and the bonds that held every molecule in its assigned place begin to let go, not all at once, but in a spreading cascade. The single coordinated thing becomes 1,000 independent things, each shard flying off on its own path, spinning, scattering, sliding to a stop somewhere on the floor. The order did not go anywhere. It did not leak out or get used up. It simply came apart, the way a sandcastle comes apart in the tide, because there are so many more ways to be scattered than to be whole that the scattering is, in the only sense that matters, inevitable. Now try, in your mind, to run it backward. Try to picture the shards finding each other again, every bond reforming at exactly the right instant, every molecule arriving back in its assigned place from a different direction at the same moment. You cannot even imagine it clearly, and the universe, in 13.8 billion years, has never once done it. Let me give you a cleaner version of the counting, because once it lands, you will never see the everyday world quite the same way. Forget the egg for a moment, and imagine a sealed box with a removable partition down the middle, and on the left side, a small amount of gas, 1 billion molecules, say, and on the right side, nothing, a vacuum. Pull the partition out. What happens? The gas rushes to fill the whole box, and it spreads itself evenly, and it stays that way. Now, ask why. in terms of arrangements. When the gas was confined to the left half, every one of its molecules had to be somewhere in that left half. That is a constraint, and constraints are rare and special. Once the partition is gone, each molecule is free to be anywhere in the whole box. The number of arrangements with the gas spread evenly through the full box is larger than the number with it crammed into the left half by a factor of 2 raised to the power of the number of molecules, which for a billion molecules is a 2 with hundreds of millions of zeros after it. The gas does not spread out because it is pushed. It spreads out because, of all the arrangements available to it once the partition is gone, almost every single one looks spread out, and only an absurdly tiny fraction looks gathered on the left. Evenness is not a force, it is a count. And the same count, run in reverse, tells you why you will wait forever for the gas to gather itself back into the left half on its own. It could happen, nothing forbids it. Every molecule would simply have to wander, by pure chance, back into the left at the same instant. The arrangement exists, it is one of the legal microstates. It is just one of the legal microstates out of a number so enormous that you would wait, on average, vastly longer than the present age of the universe to see it occur even once in a box you could hold in your hand. This is the texture of the second law. It is not that order is forbidden. It is that order is so vastly outnumbered by disorder that the drift toward disorder is, for all practical purposes, a certainty, and the drift back is, for all practical purposes, never. This is the second law of thermodynamics, and in Boltzmann's hands it stops being a mysterious rule and becomes almost a matter of counting. Entropy tends to increase, because high entropy states are simply more numerous than low entropy ones, so a system left to itself, wandering more or less randomly among the microstates available to it, will almost always find itself drifting from the rare ordered configurations toward the overwhelmingly common disordered ones. The German physicist Rudolf Clausius had stated the law in 1865. In grand terms, the entropy of the universe tends to a maximum, but it was Boltzmann who showed why, who grounded that cosmic-sounding principle in nothing more exotic than probability. The egg breaks because broken is more probable than whole, by a margin so enormous that probable becomes certain. It is worth saying a word about Boltzmann himself, because the idea cost him a great deal. In his own time, the atomic picture he relied on was not accepted by everyone. Some influential scientists doubted that atoms were real at all, and treated his statistical mechanics as an elaborate fiction. Boltzmann spent years defending the reality of atoms and the soundness of his entropy argument against determined opposition and against the reversibility and recurrence objections we are about to examine, which struck at the very foundation of his work. He suffered from bouts of severe depression, and in 1906, while on holiday, he took his own life, never having seen his ideas fully vindicated. Within a few years, the work of Albert Einstein and the experiments of Jean Perrine on the jittering of tiny particles settled the question of atoms decisively in Boltzmann's favour. The equation on his tombstone, S equals K log W, an equation he never wrote in quite that form himself, has become one of the most important statements in all of science, the bridge between the invisible world of countless molecules and the visible world of heat and order and the direction of time. Mention of this is not a detour. It is a reminder that the question we are circling tonight is not a tidy abstraction. It was hard enough and deep enough to consume one of the finest minds of its century, and it remains unresolved more than 100 years after his death. And now you can see why this looked, for a long time, like the answer to the whole mystery. Here, at last, is a direction. The forward direction of time is the direction of increasing entropy, the direction in which order gives way to disorder, in which the gathered spreads out and the concentrated dilutes. The arrow of time is the arrow of entropy. Every one-way process you have ever seen, the cooling coffee, the spreading ink, the dispersing smoke, the breaking egg, is entropy increasing, is the universe drifting from the rare to the common. It is beautiful, it is precise, it explains an enormous amount, and for these reasons most physicists, if you ask them what the arrow of time is, will tell you it is the thermodynamic arrow, the direction of rising entropy. They are not wrong, but they are not finished either, because hiding inside this beautiful answer is a flaw, a crack that runs straight to the bottom of the idea, and the people who discovered it were Boltzmann's own contemporaries, and the crack was so serious that it haunted Boltzmann for the rest of his life. Part 5. When the answer eats itself. The flaw was pointed out to Boltzmann by a colleague and friend named Joseph Loschmidt in 1876, and it is so simple and so devastating that once you see it, you cannot unsee it. Loschmidt did not deny anything Boltzmann had said. He accepted the whole picture, the microstates, the counting, the overwhelming probability of disorder. He just asked one question. Boltzmann's entire argument rests on the underlying laws of motion, the laws governing the molecules. And those laws, as we have already seen, are time reversal symmetric. They work the same forward and backward. So, Loschmidt said, let us think about what that symmetry implies for your probability argument. Here is the argument, and I want to walk through it slowly, because it is the turning point of this entire investigation. Take a low entropy state, say our intact egg, and let it evolve forward. Boltzmann says, correctly, that it will almost certainly move toward higher entropy, toward the broken state, because broken states are more numerous. Fine, but now consider this. The laws of motion are reversible. That means for every forward history that takes the egg from whole to broken, there is a corresponding reversed history, with all the molecular velocities flipped, that takes it from broken back to whole, and that reversed history obeys the laws just as perfectly. Boltzmann's counting argument cannot tell these two apart, because his argument only counts microstates, and it applies identically in both time directions. If high-entropy states are more numerous, and a system is likely to drift toward them in the future, then by exactly the same reasoning, a system is likely to have drifted toward them from the past as well. The probability argument is symmetric. It does not know the difference between forward and backward. Let me make the consequence as stark as it really is. Suppose you find a system right now in a state of middling entropy, an ice cube half melted in a glass of water, say. Boltzmann's statistics, applied honestly, predict that a moment from now it will be more melted, higher entropy. Good, that matches what we see. But those same statistics, applied with equal honesty, predict that a moment ago it was also more melted. The most probable past of a half-melted ice cube, according to pure entropy counting, is not a whole ice cube. It is a glass of slightly cooler water that, by sheer fluctuation, briefly congealed part of itself into ice. The statistics say that the low entropy past is fantastically unlikely, that the overwhelmingly probable history of any ordered thing you see is that it fluctuated into existence from disorder rather than having been more ordered before. And that is, of course, the exact opposite of everything you know. You know the ice cube was whole an hour ago. You know the egg was intact before it fell. The statistics, left to themselves, predict a past that is nothing like the past we actually have. There is a vivid way to feel the force of Loschmidt's point, sometimes called the reversibility demon. Imagine you let the gas spread through the box, reaching its even high entropy state, and then imagine a being who could reach in and reverse the velocity of every single molecule at once, leaving each one exactly where it is, but sending it back along the path it came. The laws of motion guarantee what would happen next. Every molecule would retrace its steps, and the gas would gather itself back into the left half of the box. Entropy falling, order returning, the whole spreading process running backward in perfect detail until the gas sat once more compressed against the partition. This is not a fantasy that breaks any law. It is a direct consequence of the reversibility we established at the very start. For every spreading out, there is a velocity reversed gathering up that is equally legal. The only reason we never see the gathering up is that we never get to set up those perfectly reversed velocities. The universe does not hand us that special starting condition. And there is the word again, the one that keeps surfacing. Starting condition. The arrow is not in the dynamics. It is in the conditions we start from. This is Loschmidt's reversibility paradox, and there was a second blow to follow it. In 1896, a young mathematician named Ernst Zermelo, drawing on a theorem proved by the great Henri Poincare, pointed out something else. Poincare had shown that any closed system, left alone long enough, must eventually return arbitrarily close to its starting configuration. This is called the recurrence theorem. If the universe is a closed mechanical system, then entropy cannot simply rise forever. Given enough time, the molecules must wander back, by chance, into a low entropy arrangement again, and the whole history must, in some sense, repeat. Entropy does not climb a one-way staircase. It rides an unimaginably slow wave that must eventually come back down. So even the idea that entropy is always and forever increasing turns out, on the mechanical picture, to be false in the very long run. Now, the physics has answers to soften both of these blows, and I do not want to mislead you. The recurrence time, the time you would have to wait for a room full of air to spontaneously gather back into one corner, or for the universe to repeat, is not merely long. It is so long that the number of years has more digits than there are particles in the observable universe. You would wait incomprehensibly longer than the current age of the cosmos, by factors that make the age of the cosmos look like the blink of an eye. So in practice, recurrence never happens, and the second law is safe for any timescale you will ever care about. But notice that this practical rescue does not touch the real wound. The real wound is Loschmidt's, and it is this. The statistical argument, the thing we thought explained the arrow, is symmetric in time. It explains why entropy is higher in the future. It explains, with exactly equal force, why entropy should be higher in the past. And since entropy is not higher in the past, since the past was in fact extraordinarily ordered, the statistical argument by itself cannot be the source of the arrow. It cannot be, because it does not pick a direction. It points both ways at once. Sit with this for a moment, because it is the place where the floor drops out a second time, and the second drop is deeper than the first. A few minutes ago, we had a beautiful answer in our hands. The arrow of time is the increase of entropy, the drift from order to disorder, and it felt complete. It felt like the kind of explanation you could rest on. And now Loschmidt has shown us that this answer, examined honestly, explains the wrong thing twice over. It tells us the future will be more disordered, which is true, and it tells us the past was more disordered too, which is false, and it says both with the same breath and cannot tell them apart. The single most trusted idea in all of thermodynamics, the one principle physicists will tell you can never be broken, turns out to be silent on the very question we came here to ask. It does not know why time moves forward. It cannot know, because its own foundations are as reversible as the laws beneath them. The strongest answer anyone has ever found does not, on its own, contain an arrow at all. And if you feel a kind of vertigo at that, you are feeling exactly what Boltzmann felt. The man who built this and then spent his later years defending it against precisely this objection, never fully resolving it before his death in 1906. So we are not finished, and the question has changed shape on us. We came in asking why entropy increases toward the future. We now see that the real question is sharper and stranger. Entropy increases toward the future and not toward the past. but the statistics treat the two directions identically. So the difference between them, the thing that makes the past low and the future high, cannot be coming from the statistics. It has to be coming from somewhere else, from some fact that the counting argument does not contain some extra ingredient we have been quietly assuming without admitting it. And when physicists finally pinned down what that extra ingredient is, they found that it was not a law at all. It was an assumption about how everything began. Part 6. The rescue that moves the question. Here is what saves the second law, and I want you to watch very carefully what it costs us, because the cost is the whole point. The reason entropy increases toward the future and not toward the past is not contained in the laws, and it is not contained in the statistics. It has to be added by hand as a separate fact, a fact about the initial condition of the universe. The fact is this: the universe began in a state of extraordinarily low entropy. That is the missing ingredient. That is the thing that breaks the symmetry Loschmidt exposed. Once you assume that the universe started out in an exceptionally ordered, low entropy condition, then the statistical argument works perfectly, but only in one direction. Starting from that ordered beginning, almost every possible history leads to higher entropy, because higher entropy is more probable, and so entropy reliably climbs from the beginning of time toward the future. The arrow appears, but it appears only because we put the order in at the start. It is worth being clear about why physicists accept something so unsatisfying. They accept it because, without it, the world makes no sense at all, and with it, the world snaps into focus. Every reliable inference you make about the past depends on the past hypothesis, whether you know it or not. When you see a half-melted ice cube and conclude that someone put a whole 1 in the glass an hour ago, you are not reasoning from the statistics, which, as we saw, would tell you the ice probably congealed by fluctuation from warmer water. You are reasoning from the assumption that the past was more ordered, that the ice came from a freezer, that the universe behind this moment was lower in entropy than this moment is. The same is true of every fossil, every photograph, every scar, every document, every memory. Our entire ability to know anything about history, from the geological record to last Tuesday, rests on the silent premise that entropy was lower in the past. The past hypothesis is not an optional flourish. It is the hidden foundation under all of our knowledge of what has happened. This assumption has a name. Philosophers and physicists call it the past hypothesis. The term was coined by the philosopher of physics David Albert in his book Time and Chance, published in the year 2000, but the idea is older, and one of its clearest statements came from Richard Feynman, who in a series of lectures in 1964, later collected as The Character of Physical Law, told his audience plainly that the reason for the arrow of time, the reason things are irreversible, is that the universe was more ordered in the past, and that this orderliness is not something the laws explain, but something we have to take as a given about how the world started. Feynman put it bluntly. For some reason, he said, the universe at one time had a very low entropy for its energy content, and since then the entropy has increased. That is the arrow. That is its source. Not a law. A starting condition. I need you to feel how strange a resolution this is, because it is easy to nod past it. We set out to explain why time has a direction. We examined the laws and found no direction in them. We examined the statistics and found no direction in them either. And the answer we have arrived at is that the direction does not come from any ongoing rule or principle at all. It comes entirely from the fact that one end of time, the end we call the beginning, happened to be in a very special, very ordered, very low entropy state, and the other end was not. The arrow of time is not a thing the universe keeps doing. It is a thing the universe started out committed to, the way a ball perched at the top of a hill is committed to rolling down. The asymmetry is not in the laws. We said that phrase at the very beginning, and now we can complete it. The asymmetry is not in the laws. It is in the beginning. And this should make you deeply suspicious in the best way, because look at what has actually happened to our question. We have not answered it. We have moved it. We started by asking why time moves forward, why the egg breaks and never unbreaks, why heat flows from hot to cold. And the answer, when we finally pinned it down, was because the universe began in a state of extraordinarily low entropy. But that just turns the question into a new one, which is, well, why did the universe begin in a state of extraordinarily low entropy? We have not closed the mystery. We have relocated it from the everyday world of cooling coffee and breaking eggs, all the way back to the first instant of time, to the initial condition of the entire cosmos. The locked door we were looking for has a new address. It is no longer in your kitchen. It is at the beginning of everything. You might hope, reasonably, that this new question has an easy answer, that there is some obvious reason the universe had to start out ordered. There is not. In fact, when physicists try to say just how special that initial low-entropy state was, just how ordered the beginning had to be to set up the arrow we live inside, the numbers they get back are unlike anything else in science, so large and so strange that they are difficult even to write down. We are going to face that number directly in a little while, and it is going to be one of the more astonishing things you have ever heard, because the precision required at the beginning of the universe is not just unlikely. It is unlikely on a scale that makes the word unlikely almost meaningless. But before we go to the beginning of the universe, I want to test the other two suspects, the other two popular answers, because you might be thinking that entropy and the early universe is only one way to look at this, and that surely the arrow of time has something to do with memory, with the fact that we remember the past and not the future, or with the expansion of the universe, the great outward rush of the galaxies. These are real proposals, and they deserve real tests. So let us take them one at a time. And what we are going to find, I will warn you now, is that they do not lead us out of the room. They lead us back to the same door. Every road we walk arrives at the same low entropy beginning. Let us start with the most intimate of them, the one that is happening inside your own skull as you listen to my voice. Let us talk about memory. Part 7. The arrow inside your memory. There is a powerful intuition that the real difference between past and future is about knowledge. We remember the past, we do not remember the future. The past is the realm of records, of photographs and footprints and scars and memories of things that have left their mark. The future leaves no marks, because it has not happened yet. So perhaps, the thought goes, this is what the arrow of time really is at bottom. The forward direction is the direction in which records accumulate, the direction your memory points. Time moves forward because that is the way knowledge grows, fact by fact, moment by moment, the past filling up with things we can know while the future stays blank. It is a beautiful idea, and it feels close to the truth, closer maybe than entropy, because it is so personal. But we have to ask the same hard question we asked of change. Is memory the source of the arrow, or is it a symptom of it? Does the universe move forward because we remember, or do we remember because the universe moves forward? And when you work it through, the answer turns out to be the second one, decisively, and the reason why is one of the most elegant results in all of physics, a result that ties the contents of your mind directly to the breaking of the egg and the cooling of the coffee. Memory does not explain the arrow of time. Memory runs on the arrow of time. It is downstream of entropy, and I can show you exactly why. Start by asking what a memory physically is. A memory, or any record at all, is a physical configuration of matter that reliably corresponds to some past event. A footprint in sand is a record of a foot. A photograph is a record of a scene. A pattern of connections among the neurons in your brain is a record of an experience. In every case, a record is a piece of the world that has been put into a specific, ordered, low-entropy state by the event it records, and that then holds that state. And here is the crucial thing. To create a record, to lay down a memory, you have to take some piece of matter that was in a blank, ready, low-entropy condition and write information onto it. That writing is a physical process, and physical processes that establish order in one place always pay for it by producing more disorder somewhere else. There is no such thing as a free record. Making a memory increases the total entropy of the universe, even as it creates a small island of order inside your head. There is a famous puzzle that makes this concrete, and it took more than a century to fully solve. In 1867, James Clerk Maxwell imagined a tiny, intelligent being, later called Maxwell's demon, stationed at a small door between two halves of a gas-filled box. The demon watches the molecules approach, and it opens the door only to let fast molecules through to one side and slow molecules through to the other. Over time, one side grows hot and the other grows cold, and the demon has sorted the gas, lowering its entropy, apparently for free, just by watching and choosing. If this worked, it would break the second law outright, letting you extract useful energy from the sorting forever. For 100 years, the demon haunted physics, because no one could quite say what was wrong with it. The resolution, when it came, is exactly the point we are making about memory. To sort the molecules, the demon must measure them, and to keep measuring, it must store and then erase information about the molecules it has seen. And erasing information, as we are about to learn, is not free. The entropy the demon seems to remove from the gas is paid back in full by the entropy generated in the demon's own memory. The demon obeys the second law after all, because the demon is a record keeper, and record keeping has a thermodynamic price. The man who made this precise was a physicist named Rolf Landauer, working at IBM in 1961. Landauer was studying the thermodynamics of information, and he proved something that has become known as Landauer's principle. It says that there is a minimum, unavoidable thermodynamic cost to erasing a single bit of information, a cost that must be paid by releasing heat into the surroundings. The amount is tiny, a few hundredths of an electron volt at room temperature, about 3 times 10 to the minus 21 joules for a single bit. But it is not zero, and it is irreducible. Years later, in 1982, the physicist Charles Bennett used exactly this principle to close the case on Maxwell's demon once and for all, showing that the demon's unavoidable cost of erasing its memory to make room for the next measurement always equals or exceeds the entropy it manages to remove from the gas. The books always balance. There is no free sorting, no free record, no free memory, and the reason is always the same one-way street. You cannot erase information without dumping entropy into the world. And the same logic, run in reverse, applies to writing and storing reliable records. The act of forming a memory is thermodynamically the same kind of act as the egg breaking. It is a process that can only run in the direction of increasing total entropy. Your brain laying down the memory of this sentence is, physically, on the same one-way street as the smoke dispersing from the candle. Imagine, right now, that you are forming a memory, because, in fact, you are. Picture the inside of your own head as I speak, the soft electrical traffic of it, and pick one small thing to remember, the sound of a word, the shape of an idea. Watch what has to happen for that memory to take hold. Somewhere in the tangle of your neurons, connections that were loose must tighten, proteins must be built and set in place, a pattern that did not exist a second ago must be carved into the tissue and made to stay. That is, order being created, a small, specific, low-entropy structure forming where before there was only readiness. But follow the heat. To build that structure, your neurons burn sugar and oxygen, and they shed warmth into the blood, and the blood carries it to your skin, and your skin releases it into the air of the room, and the air carries it outward, never to be gathered back. The little island of order that is your new memory is paid for exactly and unavoidably by a larger spreading of disorder into the world around you. You cannot hold on to the past without pushing the universe a little further toward its future. The very act of remembering is the arrow of time happening inside you in real time as you do it. And now you can see why memory cannot be the source of the arrow. It is built out of the arrow. The reason your records are all of the past and never of the future is that making a record requires increasing entropy, and entropy only increases in one direction, the direction set, as we have seen, by the low entropy beginning of the universe. If the universe had no thermodynamic arrow, there would be no reliable records at all, in either direction, because there would be no way to create the ordered, stable structures that records are made of. Memory does not give time its direction. The low entropy past gives memory its direction, and through memory gives you your entire sense of moving through time, your sense that the past is fixed and known and the future is open and dark. That sense is real, but it is borrowed. It is borrowed from the beginning, from the order the universe started with, the same reservoir that the breaking egg is spending. The asymmetry of your own mind, the deepest feeling thing about being a conscious creature in time, is one more thing the early universe is paying for. This also explains something you may never have thought to find strange, which is why records are always of the past and never of the future. It feels almost too obvious to question. Of course, a photograph shows a moment that already happened. Of course, a footprint marks a step already taken. But why should it be so? The laws are symmetric. Why does the world not contain footprints of steps not yet taken, photographs of scenes that have not occurred? The answer is the same one we keep arriving at. A record is a correlation between an ordered mark and an event, and establishing that correlation requires the mark to start in a ready, low entropy, blank condition, which it can only do because the past is low in entropy. The blank film, the smooth sand, the empty page, the unwritten neuron, all of these are little pieces of the low entropy past waiting to be written on. There is no corresponding reservoir of blank, ready, low entropy material in the future for the future to write its records onto, because the future is the high entropy direction. So records pile up pointing backward, all of them, every photograph and fossil and memory, like compass needles that can only point one way, and the way they point is set, once again, by the order the universe started with. Your past is knowable, and your future is not. Not because of anything special about now, but because the reservoir of blank pages lies behind you and not ahead. So the third suspect joins the others. Memory is real, memory is profound, but memory is downstream. It is a consequence of the thermodynamic arrow, not its cause, and tracing it back leads us, yet again, to the same door, the low entropy beginning. We have now tested 3 of the 4 popular answers. Time is change, and change has no direction. Time is entropy, and entropy needs a low entropy past to have a direction. Time is memory, and memory is built from entropy and inherits its direction. 3 roads, 1 destination. There is a 4th answer, and it is the most cosmic of them, the one that reaches past the kitchen and the brain and out to the largest thing there is, the whole expanding universe. Many people feel, intuitively, that the arrow of time must somehow be connected to the great outward rush of the galaxies, that the universe getting bigger is the universe moving forward. It is a serious idea, and it has been taken seriously by some of the greatest physicists who ever lived, one of whom got it memorably and publicly wrong. Part 8. The Expanding Universe. The universe is expanding. This is one of the firmest facts in all of science, established by Edwin Hubble in 1929 and confirmed in overwhelming detail ever since. The galaxies are flying apart from one another, the space between them stretching, and if you run the expansion back, you arrive at the hot, dense beginning we call the Big Bang, about 13.8 billion years ago. So here is a direction in time that is written across the entire sky. The forward direction is the direction in which the universe grows larger, in which the galaxies grow more distant, in which everything spreads out. Could this be the arrow we are looking for, the master arrow that sets all the others? Could time move forward simply because the universe is getting bigger? The idea is appealing, and in 1962, a physicist named Thomas Gold proposed a strong version of it. Gold suggested that the thermodynamic arrow and the cosmological arrow are not just parallel but linked, that the expansion of the universe is what drives entropy upward, and that the two are bound together so tightly that if the universe ever stopped expanding and began to contract, the thermodynamic arrow would reverse with it. In a contracting universe, on Gold's picture, entropy would decrease, broken eggs would reassemble, and beings living in that phase, if there could be any, would remember what we call the future and move toward what we call the past. It is a bold and beautiful conjecture, and it put a sharp question on the table. Is the direction of time really tied to the expansion of space? Before we follow that question, it is worth appreciating how natural Gold's intuition was, because it springs from a real and suggestive coincidence. We live in a universe that is both expanding and increasing in entropy, and both of these define the same forward direction of time. It is tempting, almost irresistible, to think that two arrows pointing the same way must be the same arrow, that the grand outward motion of the cosmos and the humble cooling of your coffee are two expressions of a single underlying process. Gold made that temptation into a precise scientific claim, and the great virtue of a precise claim is that it can be tested and, if necessary, shown to be false. That is exactly what happened, and the testing of it taught physicists something they would not otherwise have known. The question was taken up years later by Stephen Hawking, and the episode is one of the most instructive in modern physics because Hawking, by his own account, got it wrong. In his work on the quantum state of the universe in the 1980s, Hawking at first concluded that Gold was right, that if the universe recollapsed, time's arrow would reverse, entropy would fall, and the contracting phase would be like the expanding one run backward. He believed this for a while and argued for it. And then two of his colleagues, Don Page and Raymond Laflamme, convinced him that the conclusion did not follow from his own equations, that a recontracting universe would not tidy itself back up, that entropy would keep right on increasing even as space shrank. Hawking publicly changed his mind, and in his book A Brief History of Time, he called this mistaken belief about the arrow of time reversing one of the errors he most regretted, his greatest mistake, an admission made all the more striking by how rarely scientists of his stature say such a thing in print. The lesson Page and Laflamme drew out is worth stating carefully, because it is easy to get backward. Imagine the universe really did stop expanding someday and begin to contract, the galaxies falling back toward one another, space shrinking, temperatures rising. You might picture this as a film of cosmic history running in reverse, and you might expect, as Gold and the early Hawking did, that everything else would run in reverse too, stars unburning, entropy falling, eggs reassembling. But that is not what the equations say. As the universe contracts, the matter inside it does not smooth back out. It keeps right on clumping, keeps forming black holes, keeps growing more disordered, because nothing about contraction reaches in and reverses the local processes of gravity and thermodynamics. A recontracting universe would not be a tidy mirror of its expanding youth. It would be a hot, violent, increasingly clumped and increasingly disordered place, with entropy still climbing all the way down into the final crush. The thermodynamic arrow would keep pointing the same way, even as the cosmological arrow reversed. The two arrows, which had marched together for so long, would come apart, and that is exactly why they cannot be the same arrow. One can flip while the other holds. So what is the actual relationship between the expansion of the universe and the arrow of time? It is subtler than Gould hoped, and it is the key to the whole puzzle. The expansion does not, by itself, force entropy to increase. You can imagine an expanding universe in which entropy is already at its maximum and nothing irreversible happens. And you can imagine, as Hawking came to accept, a contracting universe in which entropy keeps rising. The expansion does not set the direction. What the expansion does is something more interesting. It provides the room, the opportunity, for entropy to keep increasing, and it does so precisely because the universe began in that special, smooth, low-entropy gravitational state we keep circling back to. As the universe expands and matter clumps together under gravity, into stars and galaxies and ultimately black holes, the entropy of the universe climbs and climbs, and there is always more room to climb into. The expansion is not the cause of the arrow. The expansion is the stage on which the arrow, set in motion by the low entropy beginning, plays itself out. And so the fourth suspect falls into line with the other three, in the same way with the same lesson. The expanding universe does not explain why time moves forward. It is, like memory, like the breaking egg, an expression of the arrow rather than its source. And when you ask where that source actually lies, you are sent back, one more time, to the condition of the early universe, to the fact that the cosmos began in a state of staggeringly low entropy and has been climbing away from it ever since. 4 answers, 4 roads, 1 destination. The locked door at the beginning of time. We have circled it long enough. It is time to walk up to it and look at exactly what is behind it, to ask just how special that beginning had to be. But before we do, I have to be honest with you about something, because there is one place, just one, in all of physics where the laws themselves seem to know the difference between past and future, where the perfect time reversal symmetry we met at the start very slightly cracks. It was found by accident, it won a Nobel Prize, and for a moment it looked like it might be the answer. Let me take you to a laboratory on Long Island in the summer of 1964. Part 9. The one crack in the laws. Everything I have told you so far rests on a single claim made at the very beginning, that the fundamental laws of physics are time reversal symmetric, that they do not know which way time goes. That claim is true to extraordinary precision, but it is not, it turns out, exactly true, and the exception is so strange and so important that we have to look at it directly. Because if there is even one place where the laws themselves distinguish past from future, then maybe, just maybe, that is where the arrow secretly comes from, and the whole story about entropy and the low entropy beginning is missing the real source. This is a serious possibility, and to address it honestly we have to go to Brookhaven National Laboratory on Long Island in New York in 1964, where 2 physicists named James Cronin and Val Fitch were studying one of the most peculiar objects in the subatomic world, a particle called the neutral kaon. The kaon is a particle that need not concern us in all its detail, but it has a remarkable habit. The neutral kaon and its antiparticle can transform into each other, oscillating back and forth, and out of this comes a long-lived version of the particle called the K-long, which physicists expected, on the basis of a symmetry they trusted completely, to decay in a particular way and never in another. The symmetry was called CP, the combination of swapping particles for antiparticles and reflecting space in a mirror. Everyone believed CP was exact, that nature did not distinguish between a process and its mirror image antimatter counterpart. And if CP was exact, the K-long was forbidden from decaying into two particles called pions. It was supposed to decay into three. The two-pion channel was simply not allowed. Picture the experiment running. In the quiet of the laboratory, the detectors watching a beam of K-long particles travel down a long evacuated pipe and decay. Cronin and Fitch are looking for the ordinary three-particle decays, cataloguing them, and they are not expecting trouble. But as the data accumulate, something is wrong. A small number of decays, about 1 in every 500, are coming out as two pions, the channel that is supposed to be forbidden. It is a tiny effect, easy to dismiss as contamination, as some flaw in the apparatus, and they do not announce it lightly. They check everything. They consider every way the beam could be dirty, every way the detector could be fooled, and one by one they rule the possibilities out. The two-pion decays are real. The forbidden channel is open, just barely, just 2 parts in 1,000, but unmistakably open, and the meaning of it, as it settles over them, is staggering. Nature does distinguish between a process and its mirror antimatter image. The symmetry everyone trusted is broken. There is a handedness, a preference, written into the deepest level of physics, where no one believed any preference could exist. It is hard to overstate how unwelcome this result was, and that is part of what makes it trustworthy. Cronin and Fitch were not looking for CP violation. Almost no one believed it could exist. The symmetry was considered a near certainty, a pillar you could build on without checking. The experiment that found the cracks in it was designed for an entirely different purpose, and the anomaly showed up as an unwanted contaminant in the data that simply would not go away no matter how carefully they cleaned the experiment. This is often how the most important discoveries arrive, not as the triumphant confirmation of a prediction, but as a small, stubborn wrongness that refuses to be explained away, forcing the world to be stranger than anyone wanted it to be. The two-pion decays were the universe insisting, quietly, against everyone's expectations, that it does keep a faint preference between one direction of time and the other. This discovery, called CP violation, earned Cronin and Fitch the Nobel Prize in Physics in 1980. And here is why it matters for us. There is a theorem, the CPT theorem, we met at the start, which says that the combination of C, P, and T together must be exactly preserved. It is one of the most ironclad results in physics. But if that full combination is exact, and if CP by itself is violated, then T by itself, time reversal, must also be violated by exactly the amount needed to keep the total intact. In other words, the discovery of CP violation was, indirectly, the discovery that there are processes in nature that are not the same run forward and backward. The kaons had revealed a tiny, genuine, law-level arrow of time, a place where the universe itself, at the level of fundamental physics, can tell the difference between past and future. Decades later, this was confirmed directly. The CPLEAR experiment at the laboratory called CERN reported direct evidence of time reversal violation in 1998, and in 2012, an experiment called BABAR at the Stanford Linear Accelerator Center watched particles called B mesons and saw the asymmetry between forward and backward processes directly and unmistakably, with overwhelming statistical confidence. So here, at last, is a law that knows which way time goes. Is this the answer? Is this the secret source of the arrow, the thing entropy was only borrowing from all along? And the answer, frustratingly, beautifully, is almost certainly no, and it is worth understanding exactly why, because the reason is instructive. The CP violation found in the kaons is fantastically tiny, a couple of parts in 1,000, and it appears only in certain exotic decays of certain exotic particles governed by the weak nuclear force. It has no detectable influence on the cooling of your coffee, the breaking of your egg, the dispersing of smoke. None of the everyday irreversible processes that define the arrow of time for you involve kaon decays at all. The asymmetry in the laws is real, but it is the wrong size and the wrong kind to be the source of the overwhelming, world-saturating arrow we actually live inside. That arrow still comes from entropy, and entropy still comes from the low entropy beginning. The kaon's tiny arrow runs alongside the great thermodynamic one, but it does not drive it. And yet the kaon's arrow may be responsible for something just as profound, something without which you would not exist to wonder about any of this. In 1967, the Soviet physicist Andrei Sakharov asked how the universe came to be made of matter at all. In the hot beginning, you would expect matter and antimatter to have been produced in equal amounts, and equal amounts of matter and antimatter annihilate completely, leaving nothing but light. A universe with no leftover matter would have no galaxies, no stars, no planets, no people, just a fading bath of radiation. The fact that there is matter at all means something tipped the balance very slightly in matter's favor in the first moments. Sakharov showed that to tip that balance, the laws of physics must satisfy three conditions, and one of them is exactly the kind of CP violation that Cronin and Fitch had found. Sakharov's three conditions are worth naming, because together they read almost like a recipe for a universe that can contain anything at all. First, there must be processes that change the balance between matter and antimatter that can create a little more of one than the other. Second, both C symmetry and the combined CP symmetry must be violated, so that those processes actually run at different rates for matter and antimatter rather than perfectly cancelling out. And this is precisely the kind of violation Cronin and Fitch stumbled onto. And third, the universe must pass through a period out of thermal equilibrium, a moment of imbalance during which the tilt can be locked in rather than smoothed away. The early universe, cooling rapidly from the Big Bang, supplied that third condition, and the CP violation in the laws supplied the second, and somewhere in the first instance the balance tipped, leaving roughly one extra particle of matter for every billion matched pairs of matter and antimatter that annihilated into light. Everything you have ever seen or touched, every star and planet and person, is made of that 1 in a billion residue, the tiny surplus that survived the great annihilation, because the laws of physics keep a faint, strange preference between the directions of time. So the lone crack in the time symmetry of the laws, the tiny arrow hidden in the decay of the kaon, may be the very reason there is any matter in the universe to make clocks and eggs and brains out of. It does not explain why time moves forward, but it may explain why there is anything here to move forward at all. And with that, having given the one real exception its full due, we can turn back to the main road and walk at last up to the door we have been circling all night and ask the question everything has been leading to. Just how special was the beginning? How low was the entropy that the universe started with? The answer is a number, and the number is unlike anything else in science. Part 10. How impossible the beginning was. We have established that the arrow of time comes from the low entropy state of the early universe, the past hypothesis, and that every popular explanation, change, entropy, memory, expansion, leads back to it. Now I want to confront the thing itself. How special was that beginning? When physicists try to put a number on how ordered, how low in entropy, the universe had to be at the start, what do they find? The person who did this calculation most famously is the British mathematician and physicist Roger Penrose, and his answer is one of the most extraordinary numbers ever produced by science, a number so large that it strains the ordinary machinery of language. But before the number, I have to clear up something that probably feels backward because it is the key to the whole thing. When I say the early universe had low entropy, you might picture it as tidy, cool, calm, neatly arranged. It was not. The early universe was a furnace, almost perfectly uniform, its matter and radiation packed together at enormous temperature in a state of near-perfect thermal equilibrium. And thermal equilibrium, for an ordinary gas, is the state of maximum entropy, not minimum. So how can the early universe have been low in entropy when its matter looks maximally disordered? The answer is gravity, and it is the single most important and least intuitive idea in this entire story. For systems where gravity matters, the rules of entropy turn upside down. A smooth, uniform spread of matter is, gravitationally, a low entropy state, because gravity is an attractive force, and it wants to pull matter together. A clumped state, with matter gathered into stars and galaxies, and ultimately black holes, is the high entropy state. Smoothness is order when gravity is in charge. And the early universe was smooth to about 1 part in 100,000, which we can still see today directly written across the sky. That smoothness is the low entropy reservoir, and it is what the whole forward march of time has been spending. As the universe has aged, gravity has pulled the smooth matter into clumps, into stars that burn, and galaxies that turn, and black holes that swallow, and at every step the entropy has climbed, away from the smooth, low entropy beginning toward an ever more clumped, ever higher entropy future. The arrow of time is the universe falling away from its initial smoothness under the pull of gravity. Penrose captured this in something he called the Weyl curvature hypothesis, the proposal that the universe began with the clumping part of the gravitational field set almost exactly to zero, perfectly smooth, and that this near-zero starting point is the true origin of the second law and the arrow of time. To see why clumping is high entropy, consider where the entropy of the present universe actually lives. In 2010, the astrophysicists Chas Egan and Charles Lineweaver carried out the most careful accounting anyone had done of the total entropy of the observable universe, and the result is illuminating. The overwhelming majority of the entropy in the universe today is locked up not in starlight, not in the warm gas between the stars, not in the relic glow of the Big Bang, but in black holes, and in particular, the supermassive black holes that sit at the centers of galaxies. Their contribution dwarfs everything else by a wide margin, something like 3 × 10 to the 104 in natural units, while the relic radiation of the Big Bang, the cosmic microwave background, contributes only about 10 to the 88, a factor of more than a quadrillion smaller. The reason is that the entropy of a black hole grows with the square of its mass, so a single supermassive black hole holds staggeringly more entropy than all the ordinary matter that could ever have fallen into it. And black holes are the ultimate expression of gravitational clumping, matter pulled together so completely that nothing, not even light, escapes. So the entropy budget confirms the strange lesson. The early universe, smooth and black hole free, was profoundly low in entropy, and the forward march of time has been, in large part, the slow gathering of that smooth matter into clumps, and finally into the black holes that now hold most of the disorder in existence. And notice something this tells us about where we are in the story. The universe is nowhere near finished. The total entropy it could eventually reach, if all its matter were gathered into black holes, and those black holes were given the almost incomprehensible spans of time needed to evaporate, is vastly larger than the entropy it has now. There is an enormous gap between the order the universe started with and the maximum disorder it could one day reach, and that gap is the room in which everything happens, in which the future continues to open. The arrow keeps pointing forward, because the spending of the initial order is still in its early chapters. We are not living at the end of the unwinding. We are living near its beginning, in the brief, bright era when there is still abundant order left to spend, which is, not coincidentally, the only era in which complex things like stars and planets and living minds can exist at all. And now, the number. Penrose asked how precisely the initial state of the universe had to be selected, out of all the states it could conceivably have started in, to be as smooth and low in entropy as it actually was. He computed the maximum entropy the matter of the observable universe could have, by imagining it all collapsed into a single, enormous black hole, and compared it to the low entropy the universe actually began with. The ratio tells you how special the beginning was, how small a target in the space of all possibilities the universe had to hit. The answer Penrose arrived at in his book The Emperor's New Mind in 1989 is that the precision required is 1 part in 10 to the power of 10 to the power of 123. Let me try to convey what that means, though I will not entirely succeed because the number defeats the attempt. It is not 10 to the 123, which would already be enormous, a 1 followed by 123 zeros. It is 10 to the 10 to the 123. The exponent itself, the number of zeros, is 10 to the 123, which is already larger than the number of particles in the entire observable universe. If you tried to write this number out in full, with 1 zero on every particle in the cosmos, you would run out of particles before you ran out of zeros by an unimaginable margin. Let yourself stand inside that early universe for a moment, in the time before there were stars. There is no up, no down, no landmark, because everything is the same in every direction. The whole cosmos glows at one temperature, a smooth and featureless light filling all of space, the same to 1 part in 100,000, whichever way you turn. Nothing has clumped yet. There are no galaxies, no first stars, no structure of any kind, only this enormous, even gently cooling glow, stretching as far as there is afar. It looks like the simplest thing imaginable, like nothing at all is happening, like the most boring possible arrangement of matter. And that is the deception. This featureless calm is the most precisely arranged, most improbable, most exquisitely ordered state the universe will ever be in. Every clumped galaxy that will ever form, every star, every planet, every living thing, every memory anyone will ever have, is going to be paid for out of this smoothness. You are standing in the reservoir. You are looking at the bank account, full, at the only moment it will ever be full, before the long spending begins. I want you to sit with that number, 1 in 10 to the 10 to the 123, not as a piece of trivia, but as a fact about your own existence. The beginning of everything was selected, out of all the ways it could have been, to a precision so fine that the count of zeros in the odds already exceeds the count of every particle in the sky. That is not unlikely in any ordinary sense. We do not have a word for how unlikely that is, and it happened. The universe really did begin in that almost impossibly ordered state, and because it did, time has a direction, and because time has a direction, you can remember and grow and act and love and lose. Every forward moment of your life is drawn from an initial deposit of order so improbable that no one has ever been able to explain how the account came to be opened. You are not separate from the great cosmic improbability at the start of things. You are one of the places it is being spent. And the question that the entire history of physics has not been able to answer, the question hiding behind the number, is the simplest one of all. Why? Why did the universe begin in a state so staggeringly, so impossibly ordered? Nobody knows. And the not knowing is where we have to go next. Part 11. The Desperate Exits. When physicists confront a fact as strange as the low entropy beginning, they do not simply shrug. They reach for explanations. And the explanations they reach for, in this case, are some of the most imaginative ideas in modern science. I want to walk you through the main ones, not because any of them is established, but because seeing what serious people are willing to consider tells you, better than anything else could, how deep the trouble really runs. When the proposed solutions are this strange, you know the problem is real. The first hope was inflation. There is a leading theory of the very early universe, called cosmic inflation, which says that in the first sliver of a second, the universe underwent a burst of staggeringly fast expansion, stretching and smoothing space enormously. Many cosmologists hoped that inflation would explain the low entropy beginning for free, that the smoothing action of inflation would naturally produce the ordered early universe the arrow of time requires, with no fine-tuning needed. It was an attractive thought. But Penrose, among others, has argued forcefully that it does not work, and the reason is a kind of circularity. To get inflation started in the first place, you need the universe to begin in a special, smooth, low-entropy patch. Otherwise, inflation never gets going. So inflation does not remove the need for a low-entropy beginning. It requires one of its own. It does not explain the order. It assumes a smaller version of the order in order to manufacture the larger one. The mystery is not dissolved. It is pushed one step further back and left there. The second idea is stranger, and it begins with a question Boltzmann himself flirted with more than a century ago. What if the low entropy past is not special at all, but simply a fluctuation? In a universe that sits at high entropy for an unimaginably long time, random chance will occasionally, very rarely, produce a temporary dip into low entropy, the way the molecules of air in a room could, in principle, once in an absurd while, all gather briefly in one corner. Boltzmann wondered whether the ordered region we live in might be one such fluctuation, a rare statistical dip in an otherwise disordered eternity. The trouble with this idea is devastating, and it has a memorable name. It is called the Boltzmann brain problem. If our ordered surroundings are just a chance fluctuation, then simple probability says that small fluctuations are vastly more common than large ones, because they require less luck. And the smallest fluctuation that could possibly account for your experience right now is not an entire ordered universe stretching back 13.8 billion years. It is just a single brain, your brain, flickering into existence for a moment, complete with all its false memories of a past that never happened, and then dissolving back into chaos. The fluctuation hypothesis predicts that you are overwhelmingly likely to be a lone, momentary brain hallucinating a universe, rather than a real person in a real cosmos. Since that conclusion is absurd, and since we have every reason to trust that our memories and observations are reliable, physicists take the Boltzmann brain problem as a powerful argument against the fluctuation idea. The low-entropy past is not a fluke. It really was the beginning, and it really was special, and we are back where we started, needing to explain it. The third family of ideas is the most radical and the most interesting, because it questions whether there is a single beginning at all. The physicists Sean Carroll and Jennifer Chen proposed, in 2004, that if entropy has no maximum, no ceiling, then a generic, high-entropy universe could spontaneously spawn small, ordered regions, baby universes, budding off from the parent, and that inside each such region, time would have an arrow pointing away from the moment of its birth. On this picture, there is no single special beginning for everything, only an endless production of local, low-entropy points, each with its own pair of arrows running in opposite directions away from it. A closely related idea was made precise by the physicist Julian Barber and his collaborators Tim Kozlowski and Flavio Mercati, who showed in 2014 that even a simple system of gravitating particles, with no special starting condition imposed at all, will naturally develop a moment of least size and least complexity, which they called the Janus point, after the two-faced Roman god who looks both ways at once. From that central point, two arrows of time emerge, pointing in opposite directions, and observers on either side would each call their own direction the future and would see the other side as their distant past. There is something genuinely consoling and genuinely vertiginous about the Janus Point picture, and it is worth pausing on what it would mean if it were true. It would mean that there is no cosmic beginning that needs special pleading, no impossibly tuned first instant for which we must beg an explanation. Instead, low entropy would be the natural condition near a certain kind of central moment, and the arrow of time would simply be the direction in which complexity grows as you move away from that moment automatically, with nothing put in by hand. On the far side of the Janus Point, there would be another universe, or rather, the same universe running the other way, with its own galaxies and its own stars and perhaps its own observers, who would call our past their future, and would no more be able to remember what we call the future than we can. Two histories, back to back, each convinced it is moving forward, each correct from its own side, joined at a moment of minimum complexity that neither could ever reach or remember. Whether the mathematics that produces this picture in simplified models truly carries over to the full, messy universe we live in is far from settled, and most physicists remain cautious. But the very existence of the idea shows how willing serious people have become to rethink the most basic assumption of all, that time has a single beginning and runs one way from it. In these pictures, the low entropy beginning is not the start of time at all. It is a special middle, a turning point, with time running away from it in both directions, and the arrow we experience is simply the local slope on our side of it. It is worth dwelling on the Boltzmann brain problem a little longer, because it is one of those rare arguments in physics that uses pure reason to rule out an idea about the entire cosmos, and the way it works is genuinely beautiful. The logic is simply that big ordered things require more luck than small ordered things, and luck, in a universe of random fluctuations, is rationed strictly by how much of it you need. A fluctuation that produces a whole galaxy is fantastically less likely than one that produces a single star, which is fantastically less likely than one that produces a single planet, which is fantastically less likely than one that produces a single room, which is fantastically less likely than one that produces a single brain holding a single moment of experience. So if the orderly scene around you were a fluctuation, the most probable version of that scene, by an overwhelming margin, would be the smallest one that could contain your present thought, a bare brain with implanted memories, hanging for an instant in the dark, with no real past and no real world outside it. Since you have every reason to believe your memories are reliable and the world around you is real and old, you must reject the premise that produced the absurd conclusion. The orderly past was not a fluctuation. It was genuinely there, genuinely ordered, and genuinely in need of an explanation we do not have. The Boltzmann brain argument does not solve the mystery, but it slams shut one of the most tempting doors out of it. And there is a fourth idea, stranger still, which asks whether the future, and not only the past, places conditions on the present. Most of physics assumes that you fix the state of a system in the past and let the laws carry it forward. But there is a formulation of quantum mechanics, developed by Yakir Aharonov and his collaborators beginning in 1964, that uses boundary conditions from both the past and the future, treating a quantum system as constrained at both ends of time at once. Some physicists have speculated that the universe might have a final boundary condition as well as an initial one, or that there might be a genuine element of the future reaching back to shape the present, a controlled kind of retrocausality. These ideas are firmly speculative, and the honest experiments forbid using any of them to send a signal or a memory backward in time. But the fact that serious physicists are willing to consider that the direction of time might be an artifact of conditions imposed at the edges of the universe, rather than a one-way street built into its fabric, tells you how unsettled the foundations remain. Look at what we have been driven to. To explain why time moves forward, the The candidate answers now include other universes budding endlessly from a disordered parent, time pointing two ways at once from a central turning point, and the future, reaching back to constrain the present. These are the serious options. Not because physicists are fanciful, but because the thing they are trying to explain, the low entropy beginning, is so resistant to ordinary explanation that only extraordinary ideas have any hope of touching it. Every one of these proposals is an attempt to avoid simply writing down, by hand, the brute fact that the universe began in an almost impossibly ordered state for no reason we can give, and not one of them has succeeded in removing that brute fact. They have only moved it, or multiplied it, or dressed it in stranger clothes. The door is still locked. We have walked all the way around the house, and we are standing in front of it again, and it is time to say plainly what is behind it and what is not. Part 12. The door left open. So let us gather everything we have found and lay it out in the open, because the shape of the answer is, in its way, as beautiful as a clean solution would have been, and far more honest. We began with the most certain fact in your life, that time moves forward, and we went looking for its source. We looked first in the fundamental laws, and we found that they are time reversal symmetric, that they do not know which way time goes. The asymmetry is not in the laws. We tested the idea that time is simply change, and found that change has no direction of its own. We tested entropy, the strongest answer, and found that it is the direction of the breaking egg, the spreading ink, the cooling coffee, and that it is genuinely the engine of the everyday arrow, but that the statistics underneath it are symmetric, that they predict a high-entropy past as confidently as a high-entropy future, and so entropy can only give a direction once you add, by hand, the fact that the universe began in a low-entropy state. We tested memory, and found that remembering is itself a thermodynamic act, that every record is paid for in entropy, that memory does not give time its direction, but borrows it from the same low-entropy past. We tested the expanding universe, and found that expansion does not force the arrow but only provides the room for it, the stage on which the falling away from the smooth beginning plays out, a lesson Hawking learned by making and then retracting his greatest mistake. We found the one true crack in the laws, the tiny time asymmetry in the decay of the kaon, and found it real, Nobel-worthy, and far too small and too exotic to be the source of the great arrow, though it may be the reason there is any matter here at all. And every road, every single one, led back to the same place, the low entropy beginning, the smoothness of the early universe, an initial state selected to a precision of 1 part in 10 to the 10 to the 123, a number whose zeros outnumber the particles in the sky. The asymmetry is not in the laws. It is in the beginning, and the beginning is exactly the thing we cannot explain. That is the answer, and I want to be honest that it is not a closing of the question, but an opening of it. Why does time only move forward? Because the universe began in a state of breathtakingly low entropy and has been climbing away from it ever since, and everything you call the forward direction of time, every irreversible process, every memory, every act of aging, is that climb, locally, in one small place. And why did the universe begin in such a state? Nobody knows. The reason time only moves forward, and the reason the universe began so impossibly ordered, are, as far as physics can currently see, the very same question, and it is unanswered. The most familiar fact in your experience, and one of the deepest unsolved problems in science, turn out to be the same fact, wearing two faces, the way the god Janus wears two faces, one turned toward the kitchen and the cooling coffee, the other turned toward the first instant of the cosmos. Think again of the egg. The egg never unbreaks. When we first said those words, many minutes ago, it was just a homely little observation, the kind of thing a child notices. Now you can see what is actually inside it. The egg never unbreaks, because broken states vastly outnumber whole ones, and the universe drifts from the rare to the common. And the universe drifts that way, rather than the other way, only because it set out from a state of almost impossible order, smoother than smooth, a 1 part in 10 to the 10 to the 123 target that it somehow hit. The whole mystery of time is folded into that one small kitchen event. Every time you watch something break and not reassemble, you are watching the universe spend, just a little, the order it was born with. The egg never unbreaks because the universe, at the beginning, was wound up tight, and it has been unwinding ever since, and that unwinding is what you feel as the passage of time. There is a particular kind of comfort in this, if you let yourself feel it, and it is not the comfort of having the answer. It is the comfort of seeing how the largest and the smallest things in your world are bound together by a single thread. The cup of coffee cooling beside you and the first instant of the universe are not separate facts. They are the same fact, near and far ends of one unbroken line. The coffee cools because the universe began smooth, and the universe began smooth because, well, we do not know. And the coffee will go on cooling regardless, indifferent to our ignorance, carrying its small share of the cosmic arrow into your evening. When you understand this, the most ordinary moments of your life take on a quiet largeness. Nothing has changed about the coffee, but you can see now what it is connected to, and the line that runs from it back to the beginning of everything was always there, whether or not anyone traced it. And consider what it would mean if time did not have this direction, if the universe had begun already at maximum entropy, smooth and even and finished, with no order to spend. There would be no arrow, and so no change that mattered, no records, no memory, no growth, no decay, no cause leading to effect. There would be no stars, because stars are gravity gathering smooth gas into clumps, a process that needs the low entropy start. There would be no life, because life is an exquisitely ordered structure that maintains itself by spending order drawn from its surroundings, by eating, in effect, the universe's supply of usable order. A universe without the arrow of time would not be a peaceful place where nothing happens. It would be a place where nothing can happen, and no one to notice that nothing does. The very fact that there is a you, listening, capable of asking why time moves forward, is possible only because time does move forward, only because the account was opened, only because the beginning was wound so impossibly tight. And here is the thought I want to leave you with as the lights go down. Everything that makes you who you are depends on the arrow we have been chasing all night. Your memories exist because making them shed heat into the world in the one direction heat can go. Your sense of moving through time, of a past behind you and a future ahead, is built from the same low-entropy order that the breaking egg is spending. You are not standing outside the arrow of time, watching it. You are one of the countless places where the universe is cashing in the order it began with. Every breath, every thought, every forward moment of your life is borrowed from the beginning, drawn from that first impossible smoothness, paid out of an account whose opening no one can explain. The motion that carries you toward the end of your life is the same motion that lets you have a life at all, lets you remember and grow and love and wonder on a quiet night why time only moves forward. We do not have the final answer. The door at the beginning of the universe is still closed, and the smartest people who have ever lived have not been able to open it. But there is something fitting, I think, in the fact that the most ordinary thing about your day, the simple forward motion of the hours, reaches all the way down to the deepest unsolved mystery in physics. It means that wonder is not somewhere far away, in a laboratory or a distant galaxy. It is in the cup of coffee going cold beside you, in the memory you are forming right now, in the fact that this moment, once it passes, will not come again. The universe began in a state of impossible order, and it gave that order to you in the form of time itself, in the form of a single direction you can travel and never turn back. Why it began that way, we cannot yet say. But that it did, and that you are here, awake, inside the spending of it, listening as the night goes still, is the kind of fact that can carry a person gently down into sleep, wondering and unafraid.